Okay, so hi again. In this talk, I'm actually replacing my colleague Viorella Diaconou. Unfortunately, at the last minute, she couldn't join us for this meeting. Viorella is a PhD student in demography at the University of Montreal, and this is part of her doctoral dissertation. The paper is co-authored, as it was said, by Robert Bobo, who is her advisor, and Giancarlo Canarda and myself, who are at INEM. So, it seems to work now. So longevity gains recorded since the 1970s in many high-income countries such as Canada and the US have been mostly fueled by reductions in old age mortality. This era is often referred as the era of delayed aging, and it is characterized by increased survivals among the olds and the oldest olds. Up until recently, age-dependent measures such as life expectancy at age 50 or 65 or other old age were usually used to record gains that occurred during this era. However, as I discussed in my previous talk, these life expectancies at an old age tend to underestimate the improvements in survival. So in this view, again, the model age at death seems to be the more appropriate measure. So fortunately, a growing number of scholars are now using the model age at death to monitor and summarize past changes in the age distribution of death. Well, in fact, this is the central tendency of the distribution. There's a dispersion that's interesting, but for now, we're at the point where we're still focusing on the central tendency of this distribution. Hopefully, in future work, we will talk about the dispersion. So, of particular interest here are the results that were already published for the all-cause of death model age for Canada and the US. So as it is written here, since 1945 in Canada, the model age at death for females increased by 9.5 years. For males, the increase began a bit later, 1970, and so far it's been increasing by 8.7 years. The figures for the US are somehow similar with slightly greater gains overall. The US started at a lower level in terms of model age at death in these earlier periods, so there was room for more improvement. So while the evolution of the all-cause of death mode is well detailed in the literature for Canada and the US, there has been no study that discussed the cause-specific model age at death. So not for Canada, not for the US, and in fact for all countries there are very, very scarce studies on this topic. Therefore, the main objective of our work here is to investigate changes in M by 5 leading causes of death in Canada and the US for each sex. So we're studying males and females separately. This work should allow us to identify if there are causes of death that have been more responsive to improvements in lifestyle behaviors and continuing medical progress and intervention. In order to fulfill our main objective of this study, we need to adapt the method for deriving the all-cause of death model age to the context of cause-specific analysis. I will be telling you a bit more about this new method that we've developed, but first let me say a few words about the data that we've used. So for Canada, the data comes from the Canadian Vital Statistics database. We were granted special access to this database in order to get detailed information on causes of death by sex, single year of age, and single calendar years. The causes of death in this database are classified according to the WHO International Classification of Diseases, And given that our study period extends from 1974 to 2011, it covers 3 revisions of this classification. The 8th revision, so ICD-8, ICD-9, and ICD-10. For the US, what's really great is that the equivalent data are not considered confidential, and therefore they are freely available online. The 5 leading causes of death that we will be examining here are listed here. So heart diseases, cerebrovascular diseases, the main categories of cardiovascular diseases, in other words, lung cancer, colorectal cancer, breast for females, and prostate cancer for males. All right. So when studying mortality by cause of death, the main variables of interest are the lifespan and the cause of death. Because death can strike at any time and from any cause, survival time X and the cause of death K are considered as random variables. 2 functions that can characterize and describe the joint distribution of X and K are the cause-specific hazard function and probability density function. The cause-specific hazard function, also known to demographers and also actuaries, I believe, and perhaps others, as the force of mortality, is in fact representative, or it's defined as the instantaneous probability of dying in a narrow age interval centered on X from this cause K in the presence of all the other competing causes of death. So the cause-specific density function, which informs us on the likelihood of death from cause K in a short interval, is equal to mu K of X times the survival function for all causes of death combined. S of X therefore depends on the all-cause force of mortality, and based on the assumption, now bear with me, that the causes are mutually exclusive, mutually exhaustive, and by making no inference on the independence of the risk of death by any of these causes, we get that mu of X equals the sum of the various forces of mortality for each cause of death. The survival function can therefore be expressed in terms of the cause-specific forces of mortality. So in order to determine the model age at death for a specific cause, what we need to do, or the key here to the problem, is to estimate these mu K of X, okay? Each one. So for each cause of death, what we did is we assumed that the observed death rates by single year of age come from a Poisson distribution, as written here, and we estimate the force of mortality right here, which is unknown. We're estimating it in the GLM framework using a P-spline approach. All right. So for a given calendar year and sex, the P-spline smooth mortality curves for each curve are equal to the smooth force of mortality, mu hat K of X, times the smooth survival curve for all causes of death. And once we know this quantity, it's very easy to identify the model age at death. It's simply the age X at which the cause-specific density force function, what was called J of X, just to make things simpler, but basically it's the death distribution where it reaches its maximum value. Because images are worth 1,000 words, here's an illustration. These are the smooth density functions for heart disease in Canada in 4 time periods, in 4 calendar years, 1974, 1989, 2004, and 2011. What you can see is that these curves all moved towards higher ages over time, and also the model ages at death, the successive model ages at death values increased from 84.46 years in 1974 to 98.88 in 2011. So what we did basically is that we've done this analysis for each cause of death, each of the 5 leading causes of death, for each calendar year, for each sex. So let's start by looking at the results, the trends in the model age at death over time for each of the causes, sex, and countries. We start with Canada. So these are the trends in M. The figure on the left shows that since the mid-1970s, males typically die earlier from lung cancer, which is shown in green here, than for any other leading causes of death in Canada. In 1974, most males that were diagnosed with this type of cancer perished at around 70 years, whereas the model age at death for all the other causes studied was much higher than 70 years old. At the other end of the spectrum, you have cerebrovascular diseases, which was slightly above 80 years. But over time, as you can see, the increase in the model age at death for heart disease was slightly faster, and it caught up with the cerebrovascular diseases. Over this time period, the model age at death for the different causes increased by at least 7 years. For females, the figure is somehow similar. The levels are not exactly the same, but lung cancer, again, is at the very bottom of the spectrum for most of the period, and cerebrovascular disease and heart diseases are at the top. So what could be the explanations, for instance, for having lung cancer here at the bottom and these cardiovascular diseases at the top? So this is just purely speculating here, but the relatively low model values for lung cancer for both sexes may be due to the greater lethality of the disease, or perhaps because the diagnosis often occurs at a later stage when treatment options are quite limited. On the other hand, the relatively high value for cardiovascular diseases could be explained by the rapid development, especially during the earlier decades of this period, the rapid spread of treatment options, of surgical procedures, and by public health measures promoting healthier lifestyles. So while the various curves for the different causes differ greatly in terms of level, their upward trends over time are, I would say, strikingly parallel. And this is the first thing that we noticed when we plotted these trends on these two graphs. This suggests that for each sex, the sustained increase over time in the model age at death occurred roughly at the same pace for most leading causes of death in Canada since the mid-1970s. And the way we see this as being extremely positive in terms of potential for future longevity gains. But the obvious question here is this only for Canada, or are we seeing it in other countries as well? So are the trends also mostly parallel in the US, let's say? Here's what you get. So quite similar. In general, you see the same hierarchy between the 5 leading causes of death, and the parallelism of most curves seems to be holding here as well. So this is ongoing work. The conclusions for this talk are the following. Model ages at death for the 5 leading causes of death in Canada and the US followed a steady upward trend, pretty steady, since 1974, and the pace of increase was highly similar for the various causes. I have to say that this is something that we did not expect to find. Let me explain why. So because our data series starts in the mid-1970s, this is a time when the cardiovascular revolution, so the period where we were making extremely substantial gains in terms of cardiovascular mortality, was in full swing, and therefore we were expecting to find faster increases in the model age at death for these cardiovascular diseases, and somehow slower increases in terms of the model age at death for cancers. And the opposite, vice versa, in recent years, as the cardiovascular revolution somehow reaches its end, and slowly, but hopefully surely, the cancer transition is starting to pick up. So, all in all, these unexpected, I think, pleasant findings may provide important insight for the future trends in human longevity, especially if the rise in the model age at death for the various causes is accompanied by decreasing levels of old age mortality in recent years. So say that we are in some kind of shifting, everything is just shifting towards older ages for all causes of death. We plan to look into this more closely in the near future. So this is it for now. Thank you very much for your attention.
Yes?
My question it's maybe in another direction, but you have compute all the data of Canada and USA.
Yes.
It's possible to compute the data and related all the data in the state level, for example, in the USA. There is vast data
Yes.
available.
Yes, so what you're suggesting is why not look into the regional part. And we can do the same for Canada, in fact, because of course we have fewer units, geographical units in Canada. We have 10 provinces.
My idea is that in USA it's a big country, and maybe in the 50 states there is difference because of the diets, etc., etc.
Yes,
in some of the diseases.
There is a great body of literature that shows that, in fact, in the US, in terms of life expectancy at birth or even life expectancy at an old age, there are huge discrepancies. So the subgroups of the population that are performing the worst versus those who are performing the best, there can be like 30 to 40 years of life expectancy at birth gap. So this is huge. We haven't done it for the US. We have done some work for Canada, but this is definitely something very interesting to look into. Yes.
If you try,
it's possible to use the data, the available data.
The data are there. The other advantage in the US is that the National Health Center for Statistics centralizes all the data. So you might not have exactly the same quality of the data in the different states, but it's centralized, and therefore it promotes this comparability. Also, each geographic unit is not too small, because the US is a very large population. So these are two very great advantages for using the US as a study population.
Thank you.